Hello everyone. So I hope you are already aware with the equations that are used in Venn diagram optimization. If not, then first of all let us read the question that has been given to us, and then I'll explain to you that how to use the equations involved in Venn diagram optimization to solve the questions. So the question here is, in a class of 50 students, 34 students like football, 26 students like cricket and 16 students like hockey. It is known that at least one student likes only football, only cricket and only hockey. Similarly, at least one student likes both football and cricket but not hockey, both football and hockey but not cricket, and both cricket and hockey but not football. Further, at least one student likes all the three sports. Each student likes at least one sport. So all these statements that have been given to us, basically these are generally denoting or telling us what can be the possible values of all the regions in a Venn diagrams. Now we have three games involved over here, which are football, cricket and hockey. So very clearly we'll be making a Venn diagram of three sets. Then rest of the lines or rest of the statements that have been given to us, they are telling us the possible values of a particular region. So first of all, let us read the questions that have been given to us. First one is, what is the maximum number of students who like all three sports? So we'll solve this. Second one is, what is the maximum number of students who exactly like two sports? So whenever there are questions on minimum, maximum, then those are generally based upon Venn diagram optimization. Third one is, we have some additional information over here. Exactly 8 students like all the three sports. Then what can be the maximum value of sum of the number of students who like both football and hockey but not cricket, and the number of students who like both cricket and hockey but not football? So again we have the word maximum over here, so it means that this is based upon optimization again. Then in the fourth question also we have been given some additional information. Exactly 8 students like all three sports. What can be the maximum number of students who like both football and cricket but not hockey? Again the word maximum is over here, so this question is again on optimization. Now let us go to the next slide. I'll explain to you what are the equations that are involved in Venn diagram optimization, and then we'll use them to solve these questions. See, we have a three set Venn diagram over here. So let me draw one first. This will be our three set Venn diagram. One for cricket, one for hockey and one for football. Let this be the universal set. Let me call it X. Let me name the regions over here. So this will be A, B, C, D, E, F, and this will be G. This N will be the number of people who lie outside the set or who are not playing any of the games. So how can I write the universal set X over here? If I write X, then it will be equal to A plus B plus C plus D plus E plus F plus G plus N. I hope this is clear. Now if I try to look at this bracket over here, A plus B plus C, then what is A plus B plus C in the diagram? A is over here, B is over here, C is over here. So basically A, B, C are the regions that are denoting exactly one. That means the people who are playing exactly one of the games, either football or hockey or cricket. So this can be written as exactly one plus, how can D, E, F be written over here? D is over here, E is over here, F is over here. So D, E, F together, they are denoting the total region of people who are playing exactly two games. So this bracket D plus E plus F can be written as exactly 2 plus, what is this G over here? Let me write this G also. G is the region denoting people who are playing all three games. So this will be written as exactly 3 games plus none will be written as N. So we have an equation over here which is of universal set X equal to exactly 1 plus exactly 2 plus exactly 3 plus none. This equation will be very useful to us in solving questions based upon Venn diagram optimization. There is one more equation which is used, which is called S. S is nothing but the sum of values of all the sets. So S will be sum of set of football plus cricket plus hockey over here. What are the variables or numbers that are falling into set F? They are A, D, E and G. So let me write A, D, E, G over here. Then what are the numbers or variables that are falling into set C? They are D, G, B, F. So D, B, G, F are the numbers falling into set of cricket. Plus what are the numbers that are falling into, or the variables that are falling into set of hockey? They are E, G, F and C. So E plus G plus F plus C. Now if I rearrange them to write the equation in form of exactly 1 plus exactly 2 plus exactly 3, then I can rewrite it as A plus B plus C plus 2 times D plus E plus F plus 3 times G. So S will be equal to exactly 1 plus 2 times exactly 2 plus 3 times exactly 3. This will be the another equation that will be helpful to solve questions upon Venn diagram optimization. So we'll be using both of these equations. I hope you understood how we derive these. So we'll be using only these equations now. Let me remove everything else. I'll just be keeping the equations. Now the question that we have is, what is the maximum number of students who like all three sports? So we need to maximize exactly 3. We need to find out the maximum value of exactly 3. We already know that this 1 over here, it denotes all the students that play exactly 1 game. This 2 denotes all the students who play exactly 2 games. 3 denotes all the students who are playing exactly 3 games, and this n means none. That means all the students who are not playing any of these games. When we read the set, in the last line it has been given to us that each student likes at least one sport. So that means the value of n over here will be equal to 0 because each student is liking at least one sport. So n will be 0. That means there will be no student who is not liking any of the sport. So we can remove this n from this equation. N will be equal to 0. Let me remove it. Now we can move ahead with these two equations. We know that in the question it was given to us that in a class of 50 students, that means our universal set consists of 50 students. So the value of this x will be equal to 50. 34 students like football, 26 students like cricket and 16 students like hockey. So we have been given the total number of people in every set. So S was nothing but the sum of values of all the sets. So S will be equal to 34, which is the value of football set, plus 26, which is the value of set of cricket, and 16, which is the value of set of hockey. So we can write S equal to the sum of 34 plus 26 plus 16, which gives us nothing but 76. So now we have these two equations with us. Let me just subtract equation 1 from equation 2. So when we subtract equation 1 from equation 2, we get 26 equal to exactly 2 plus 2 times exactly 3. So we have this equation now. We need to maximize exactly 3. So if I need to maximize this, it is very clear that I will have to minimize exactly 2. Because in a linear equation which involves two variables, if you want to maximize one of the quantities, then other will definitely decrease. So if we maximize exactly 3, we'll have to minimize exactly 2. So what can be the minimum value of exactly 2 over here? This exactly 2 means all the students who are liking exactly 2 sport. In the question it was given to us that it is known that at least one student likes only football, only cricket and only hockey. That means this is the minimum value of exactly 3. Similarly, at least one student likes both football and cricket but not hockey, both football and hockey but not cricket, and both cricket and hockey but not football. So the minimum value of all the regions that are denoting exactly 2 will be 1, 1, 1. And the minimum value of region of exactly 3 is also 1. So if I find out the minimum value of all the regions of exactly 2, it will be equal to 1 plus 1 plus 1. So it will be equal to 3. So let me write 26 equal to 3 plus 2 times exactly 3. We have written down 3 as the minimum value of all the regions of exactly 2. Now if I calculate this exactly 3, then it will give us the maximum value of exactly 3. So if I calculate it, it will be equal to 23 by 2. So we are getting exactly 3 maximum equal to 23 by 2. But since this exactly 2, exactly 3, exactly 1 are the number of students, and 23 by 2 will be equal to 11.5. So can the number of students be 11.5 or a decimal? No, it should always be a positive integer, or we can say that it must be a natural number. So what can be the minimum value of this exactly 2 over here such that this exactly 3 becomes a natural number? So we can write 26 equal to exactly 2 plus 2 times exactly 3. So what should be the minimum value of this exactly 2 so that this exactly 3 becomes a natural number? We can give it value 4 over here, because minimum was 3. At 3 we are not getting exactly 3 as a natural number. So we can give minimum value 4 to exactly 2 so that we can make exactly 3 a natural number. So we can say that now 2 times exactly 3 will be equal to 26 minus 4, and this will give us exactly 3 equal to 26 minus 4 is 22. 22 by 2 will be equal to 11. So the maximum value of all the students who like all 3 games can be equal to 11. How did we do this? We had two equations, one for x, which is the universal set, one is for sum of values of all the sets. We subtracted equation 1 from equation 2, we got this equation over here. To maximize exactly 3, we minimize exactly 2. We know that minimum value of exactly 2 could be 3, but putting minimum value of exactly 2 as 3, we are not getting exactly 3 equal to a natural number. So we increase its value to 4, and putting exactly 2 equal to 4 over here, we are getting exactly 3 equals to 11. So 11 will be the correct answer to this question. This question was to make you understand how to solve these questions. Now we'll be applying the same concept in every question. Let us go to the second question now. I hope this one is understood. In the second question we have, what is the maximum number of students who like exactly 2 sports? See, in the last question we had an equation that 26 equal to exactly 2 plus 2 times exactly 3. In the last question we needed to maximize exactly 3. Now we have to maximize this exactly 2 over here. So that means we'll have to minimize this now so that we can maximize exactly 2. So what can be the minimum value of exactly 3? We know that it was given to us each student likes at least one sport, and it was also given to us that further at least one student likes all 3 sports. So at least one student like all 3 sports, that means the minimum value of exactly 3 will be equal to 1. So let me put 1 over here. 26 will be equal to exactly 2 plus 2 into 1. Exactly 2 will come out as 24. So the maximum value of the number of students who like exactly 2 sports will be equal to 24. So option B will be the correct answer. I hope this is understood. This is exactly like the previous question, but now here we need to maximize exactly 2. So we minimize exactly 3. Minimum value of exactly 3 is equal to 1, which has been given to us in the question. At least one student likes all 3 sports. So the maximum value of exactly 2, or the number of students who like exactly 2 sports, will be equal to 24. I hope this is understood. Let us solve the next question now. The third question. In the third question we have been given some additional information that exactly 8 students like all 3 sports. So exactly 8 means we have to take the number of students who like all 3 sports as exactly 8. We cannot minimize or maximize it. So the question is, what can be the maximum value of sum of the number of students who like both football and hockey but not cricket, and the number of students who like both cricket and hockey but not football? So let us first draw the Venn diagram and try to find out where do these regions lie. So this is the Venn diagram that we have. We have been given that exactly 8 students like all 3 sports. So we'll write 8 over here. We need to find out the regions both football and hockey but not cricket. So where is this region? Football and hockey but not cricket. This region is over here. This one that I'm darkening with red color. This is the region. And the number of students who like both cricket and hockey but not football. So both cricket and hockey but not football, where is this region? it is over here. This is the region, both cricket and hockey, but not football. So let me provide some names or variables to all the regions first. Let this be X, let this be Y, let this be Z. We know that the value of set of football, which was given to us over here, that 34 students like football. So the value of whole set of football must be equal to 34. So this region over here, it must be equal to 26 minus X plus Y. So if you add all the regions in the set of football, you will get 34. Similarly, 26 students like cricket. So the sum of values of all the regions in set of cricket must be equal to 26. We already have 8xz in the set of cricket. So this region must be equal to 18 minus x plus z. I hope this is understood. Similarly, in the set of hockey, we have been given that 16 students like hockey. So the sum of all the regions in hockey must be equal to 16. We already have 8, y and z over here. So this will be equal to 8 minus y plus z. I hope this is also understood. So according to the question, we need to find out the maximum value of sum of the number of students who like both football and hockey but not cricket, and number of students who like both cricket and hockey but not football. So we need to find out the maximum value of y plus z. This is what we need to find out. So let us find out the regions which involve y plus z first. So we can see that we have such a region over here, 8 minus y plus z, and this region denotes the people who are playing only hockey. It was given to us in the beginning of the set that it is known that at least one student likes only football, only hockey and only cricket. So what can be the minimum value of people who play only hockey? It will be equal to 1. So 8 minus y plus z can have minimum value 1. So what can be the value of y plus z so that we get 1 in RHS? It must be equal to 7. So this is what we need to find out, maximum value of y plus z. So maximum value of y plus z will be equal to 7. See why we did this? We had a region of 8 minus y plus z over here in the set of hockey. We can find out the maximum of y plus z if we minimize the value of this region over here. So what is the minimum value of this region over here? It was equal to 1 because it was given to us that at least one student likes football, only cricket and only hockey. So we put it equal to 1, we get y plus z equal to 7. So 7 will be the correct answer to this question. So option B is the answer. I hope this is understood. Let us try to solve the next question. Fourth question is, again we have an additional information first. Exactly 8 students like all 3 sports. Question is, what can be the maximum number of students who like both football and cricket but not hockey? So let us again draw the diagram first. So this is the diagram that we'll have, the same diagram like the previous question, but here we need to find out the maximum number of students who like both cricket and football but not hockey. So where is such a region? We have such a region over here, both football and cricket but not hockey. So we need to maximize the value of x. See, if we look at the regions x, y and z, then what are these regions? These are the regions denoting exactly 2. So let us use the equations that involves exactly 1, exactly 2, exactly 3, which was, first one was universal set which was equal to 50 equal to exactly 1 plus exactly 2 plus exactly 3. We have been given the value of exactly 3 equal to 8 over here. So let me write 8 over here. So we get exactly 1 plus exactly 2 equal to 42 over here. We have another equation as well which was equal to sum of values of all the sets. It was equal to 76 exactly 1 plus 2 times exactly 2 plus 3 times exactly 3. Again the value of exactly 3 is equal to 8 over here, so we'll write 3 into exactly 3, 3 into 8 over here. So if we solve this equation, we get exactly 1 plus 2 times exactly 2 equal to 76 minus 24, which gives us 52. So now we have these two equations. We have these two equations involving variables exactly 1 and exactly 2. We can cancel the variable involving exactly 1. So if we subtract equation 1 from equation 2, then we get exactly 2 equal to 10. So exactly 2 can also be written as x plus y plus z. This is equal to 10. We need to maximize x. So definitely we'll have to minimize y and z. Then only we'll be getting the maximum value of x. So can you tell me the minimum value of y and z? What is y? Y is the number of students who are playing football and hockey but not cricket. And Z is the number of students who are playing cricket and hockey but not football. So it was given to us in the question that at least one student likes both football and cricket but not hockey, both football and hockey but not cricket, and both cricket and hockey but not football. So that means the minimum value of x, y, z can be equal to 1. So minimum value of y will be equal to 1 and minimum value of z will also be equal to 1. So we can get x max plus 1 equal to 10, which will give us the maximum value of x equal to 8 to us. So 8 will be the correct answer to this question. I hope you understood how we proceeded. First of all, we needed the maximum value of x. So we collected all the regions involving exactly 2. So we wrote down these two equations. We found out exactly 2 equal to 10. Exactly 2 could be written as x plus y plus z, and we get it as 10. To maximize x, we need to minimize y and z. So what are the minimum value of y and z? They are equal to 1. So we put them into the equation. We get x max equal to 8, and that is what we need to find out. I hope the solution is clear to you. These are the two equations that we'll mostly use in solving questions on optimization. If there's any doubt, you can ask again. Thank you.